All right, so last class we left off with an equivalent circuit of generator. And now what we got to do is figure out what the R's and the X's of those generators need to be. So remember, that generator is a big hunk of iron with windings and coolant and all those different things, and it's spinning along. But for most purposes, all we really care about is what that voltage source is going to be approximately, as well as the inductance and the resistance of the generator. That's how we'll analyze the systems. Our mechanical engineering friends are really interested in all the mechanical portions of it. But from an electrical standpoint, if we're looking at the electrical world, that actually doesn't help us out at all. Okay. So we're going to figure out how to do some testing on it. And the tests are going to be pretty similar to what we did when we looked at transformers. And we'll do a bunch of different tests. So move this over here. So we're going to have to get our synchronous reactance and our armature resistance with the fact that you're going to have some saturation. Higher levels of excitation current are going to result in not as high or correspondingly as high values of armature or field voltage. And so we're going to do the same test we did with the transformer, open circuit and short circuit. But we're going to add one additional test. And that's the DC test, because we really have no way of teasing out what the resistance is. And that's not a problem, because if our generator shorts out and we have some resistances, as long as we're just measuring the resistance, it's no big deal. With the transformer, because we're trying to reflect primary impedances and secondary impedances, and you have to do that magnetically, you can't run DC. But over here, we're only looking at the equivalent circuit for the stator winding. We don't have to reflect any magnetic energy between the two, so we can certainly use the DC test. So let's show some tests. Let's start off with what's going on here? This is the open circuit test. Why do I have the DC stuff in here? That's not, oh yeah, okay, sorry. All right, so when we run the open circuit test, again, we have to have the rotation. So the generator has to be spinning at approximately rated speed. Just like the case of the transformer, for the open circuit test, it has to be running no load, which is another way to say no external connection or open circuited. We're going to adjust our field current. Remember that field current is the DC current that goes into the field windings or the rotor windings, and we're going to gradually increase it. We'll start off at 0, go to 1, 2, 3, 4, on and on and on until we get, so the machine is fully, at its peak value. And then we're going to plot that curve. All we're going to do. We're going to plot a curve that looks like this. IF, and this here is EA. Why do we call that EA? Well, remember, our equivalent circuit, this is JXS, this is RA. If there's no load on there, I can measure this terminal voltage. No load means I is equal to 0, which means EA is going to be the same as VT, right? So running it under no load condition means I get no voltage drop, so I'm directly measuring the value of EA, okay? But all I can get is the open circuit characteristic, or the OCC. That's what I do for the open circuit test. Let's go to the short circuit test. So the short circuit test, let's show my equivalent circuit. I'm going to do exactly the same as I did in the open circuit test, but instead of running it open circuited, I'm going to do short circuited. So I know that my terminal voltage is going to be equal to 0. The current through here does not equal 0. So that means that there's a voltage drop across there, which means this is my EA. So VT does not equal EA. But what can I get? Well, I'm going to go ahead and do that same plotting for my field current, and I'm going to go ahead and vary the current. But instead of measuring VT, I'm going to measure the armature current. And when I do that, I'm going to get a curve that looks like this. This is field current, and that is armature current. This is the short circuit characteristic of the generator. All right. So I have an open circuit and I have a short circuit. Now, the last test that I'm going to do is the DC test. And the DC test is going to vary. So remember, a DC test, the machine is not running. All I'm going to do is look at the windings. And if it's Y connected, I'm going to put DC here. So this is RA, this is RA, because my inductors are shorted out, right? If you hit an inductor with DC in steady state, that inductor looks like a short circuit. So all I have is my armature resistance. And if I can measure VDC and IDC, then RA plus RA is equal to VDC divided by IDC, right? You can see two resistors. If it's delta connected, and I do the same test, now what do I see? Well, I can see that I have an RA here, an RA here, and an RA here. Isn't that really looking like this? RA, RA, RA. When I just run the DC test, and I don't have three-phase DC, I only have single phase, but when the machine is internally connected, all three of those are there. So VDC divided by IDC is going to be equal to 2RA in parallel with a single RA, right? So if I do product over sum, that's equal to 2RA squared over the sum. So it depends on the application. If I have a delta connected generator, when I perform my DC test, then I have to take VDC over IDC, multiply that by 3/2, and I get RA. This is for delta. For Y, what I see is I've got VDC divided by IDC times 2. That's equal to RA. That's what those show here. Okay. Questions on that? Make sense? Don't make sense? All right. So I have part of my machine. I know RA. Do I know XS? No, I don't. But what I have is two curves. I have my open circuit characteristic, which is a plot of IA versus VT or EA. It's the same thing. And I have IA, IF, sorry, versus IA. And that's my short circuit characteristic, right? So if I take my V open circuit characteristic and divide by my I short circuit characteristic, I'm going to get a value of Z, right? And that Z, the magnitude of that Z, is going to be equal to that value squared. So if I want to solve for XS, that's going to be equal to the square root of Z, magnitude squared minus, not plus, RA squared square rooted, which really just means X of S is going to be equal to V open circuit divided by I short circuit, that quantity squared minus RA squared. All right. Now you got to be careful when you compare V open circuit and I short circuit. you've got to make sure these are both single phase voltages or single phase quantities, single phase voltage and single phase current. Most of the time, this VT is going to be equal to a line voltage. So if you have a Y connected machine, you need to modify that. V open circuit divided by the square root of 3, divided by I short circuit. And that's how you can solve for excess. Now, the problem is my open circuit characteristic a perfectly linear curve? Survey says no. So I have to get two values. Do you remember the data sheet that we looked at on the last class? Remember we had two values of X? We had an unsat and a sat. We have an unsaturated value and a saturated value. So what you need to do is look at your curve, and we'll call this IF1. We'll call this IF2. Those have to be the exact same point on my short circuit characteristic, and I'm going to read these values there to come up with my voltages and my currents. So the only way you can get impedance is you have to run both tests, open circuit, short circuit, and then correlate the points based on the field current to be able to get your values of X. Okay? So that's the handwork. Let's go back to the presentation. You've got RA. Here is the information sort of laid out. Let me see if I can move that here a little bit. And you can see I've got the open circuit and the short circuit characteristic. There's one other interesting piece of information. It's called the air gap line. The air gap line is essentially a straight line that if saturation never occurred, that would be the value that you attain. Okay, it just basically is a linear line the whole way. But we do have saturation. We only get it on the open circuit characteristics. We don't get it on the short circuit characteristics. And then we plot, and then we compare. We have an unsaturated value for field current and a saturated value for field current because this voltage is unsaturated and this one is saturated. The current is never saturated. And so now we can calculate here. Here's our Z-sec, and then here is our value to go ahead and calculate. That shows you for unsaturated. If you want to make a simplification, you normally can neglect RA, and you can just go ahead and solve for XS. So if you haven't performed a DC test, you can go ahead and get your values there. All right. So here's the saturated, here's the unsaturated. You can see our equivalent circuit phasor diagram. We calculated those values that way. So we like real world stuff, right? I was teasing the students that were here just a couple minutes before class. Here's real world. Estimated, not actual. So whoever makes this generator is going to assume that these are the curve characteristic. And you can see 4-pole, 1800 RPM, 1500 MVA generator. This is a big generator, right? It's 24,000 volts. It's rated at a 0.9 power factor. It's giving you an SCR, and we'll learn about that and what the short circuit ratio means in a minute. Remember I talked about really big generators need to be cool to reduce their friction and windage losses by hydrogen. What is H2? Hydrogen, right? Hydrogen in its natural form. You can't do H1 because it's not stable. And then you don't really care too much about the excitation, but just for giggles, 590 volts excitation, that's the nominal DC voltage that goes to the field winding. It also gives you some information about temperature and all that stuff, but moving down to the actual curve, we have a no load current. So this is operated at no load. Jeez, I can't talk. And this is how much field current it pulls under no load. So you need almost 2,000 amps at 590 volts DC just to produce 24,000 volts under no load. Under full load conditions, now we're pushing, we need about 6,500 amps of DC current. Okay. And then We have our rated armature voltage. So this is the nominal voltage. This is line to line voltage. So it's 24,000 volts. And look at the current, 36,000 amps of what this generator can provide under full load conditions. This generator can probably provide the whole state of Maine for its load. And definitely like Boston and all that stuff. If you look at all of New England, I think the peak demand in New England is 26 gigawatts or so, give or take. So you would need about 15 to 20 of these to go ahead and provide all of the power demand for New England. But let's see if I'm telling you no lies. What do you know? A is our air gap line. Take a look at the legend. Look at B. B is our no load saturation. Right? So that's under no load. This is another way to say open circuit characteristic. You actually have the open circuit characteristic shown on this machine. Let's keep going. Synchronous impedance. That's just a parameter that talks about X sub S. You don't have to worry about that. D is saturation at rated armature current. So that's a saturation value. Why aren't you moving up? And then we have E and F, which are saturation at rated value. So this one does not include the short circuit characteristic, does it? Right? It's not shown there. But you got an open circuit curve. Let's take a look at another example. And this one might be important to you, whether you have a homework on it. Where is, oh, guess I don't have it. Whoops. It did it again, you sneak. It's just this setup. I don't know why. But why does another display not work? I mean, it's just this one.
It's something with the answer. Yeah.
Hit duplicate. It doesn't want to do anything. So I'll try PC only, and then I'll try duplicating it again. Re-handshake. Re-say hello. Oh, now it's bringing up all kinds of weird stuff. I don't know what's on. All right, so let's take a look at our pump storage facility. So you can take a look. This is older, right? 2010, with that one that I gave you, the estimated one was, I think, 2019 or 2018. Alstom made the generator. This generator was rewound to get a little more oomph out of it because they actually had more capacity than they expected. Skip that part. You can take a look at it. That's called a snow cone, which is a generator capability curve. We may learn more about that. These are V curves. V curves are only applicable for synchronous motors, but a synchronous machine can operate as a motor or a generator. It just basically tells you what the armature current needs to be to provide a certain power factor at rated load. And you can see they look like the letter V. That's why they're called V curves. And then lastly, what do you know? If you look closely, no load voltage, open circuit, short circuit. And you can see curve number 1 is the OCC. Curve number 2 is the SCC. Number 3 is just the air gap line. So these are exactly the curves. And this is actual test data. And you'll notice here, this starts to saturate here. So if you're in this region down here, you're unsaturated. And over here, you're saturated. Okay. You'll notice something interesting about it. This says per unit. Another way to say per unit is this is either 13.8 kV or 12,844 amps. So it's a clever way to put the open circuit and short circuit characteristics on the same curve. Because if you want to put 13,800 on a curve that goes to 12,844 0.44, you might have a difference. So they just normalized everything to per unit. If you look over here on what we were just looking at, where is, oh, over here, they also do the same thing here. This is per unit voltage and current, but I actually don't necessarily see, I don't see, unless curve C is mislabeled because it says synchronous impedance. I don't know what that is. But it gives you rated voltage and rated current. So you just take that per unit number that you see, oops, here, and you either multiply that by 13.8 kV or 12,844 amps. Okay. So just a way to go ahead and do that. So I'm going to ask you for XS unsat and XS sat for this particular generator. Okay. And then, since you guys love to check your work, you can check your work. It tells you the generator electrical characteristics right here, right? So look at all the values. Obviously, we don't care about C, but look at our direct access saturated and unsaturated reactants. These are the values that you would use. So you know what the answers need to be. Okay. The only problem is it might be a little bit ambiguous to understand because it says it's in percent. I will tell you, if you multiply that value by 13.8 kV squared divided by, let me see what the power rating is in this one. I can't remember off the top of my head. I think it's 289. Oh, where are you? 307. Sorry. So if you divide that by, or multiply those two numbers, you should be able to get a comparison. Don't forget, this is a Y-connected generator. So you need to be able to divide phase voltage by phase current to get the right values. So if you're going to multiply by 13.8, that's okay. But don't forget, at some point, you're going to have to divide that by the square root of 3. Right? So the harder part about this curve is picking points to come up with your saturated and unsaturated values. Okay? But like I said, this is real world stuff. It's a data sheet that I got. It's been quite a while since I worked on this project, but this is the actual calculated. See, this is even calculated electrical characteristics of the generators at Northfield Mountain. So these generators, I don't know, 10 or so years old. But you can take a look at all the different characteristics. That's the one that you'd actually find. And you have this data sheet already available to you. I believe it should be online and accessible as of now. Questions on how to do that? Not a clue how to do that? It's the wrestling part with it. But it literally is just ignore any value of RA and literally go through our calculations that we had over here. Just find consistent field currents for it and then divide the voltage by the current. That's going to give you a ratio. Or if you multiply by the 13.8 with the square root of 3 and then divide by the 12,844 amps, you're actually going to get something in ohms. If you want to compare it to the values that we had, oh, I forgot to tell you, these values over here, these are in percent, right? So it's 1.12%. So that's 0.0112 is what you need to multiply, 0.0112 or 0.0122. So don't forget, these you have to divide out the percent. You have to get rid of the 100 that's been multiplied. Okay. So yeah, just a good little one. And next week's our last week before break, right? So I think I have it due on Thursday, so you won't have to worry about it over break. And then we can draw, once we have our values for RA and XS, we can go ahead and determine our phasor diagram based on power flow. We know that our voltage is going to be at an angle of 0, right? And we have a lagging current, because we can see that the current lags the voltage here. Then we see that our voltage drop across IA, RA, or RA is going to be in phase with the current. And then we have to rotate by 90 degrees because the inductor has magnetic. So we rotate it by 90 degrees and then we end up adding those voltages. And then this is the field voltage. So this more likely than not is going to be equal to basically just running it under very lightly loaded conditions, under no load essentially. Because EF and VT are the same. So here's our short circuit ratio, and it's just a ratio. It's defined as the ratio of field current for the rated voltage at open circuit conditions to the field current required for rated armature current under the short circuit conditions. So you have to come up with, here's my rated voltage. So I pull that, and then this is my field current to get to rated voltage on the open circuit line. Here's my rated current on the short circuit condition. So I'm going to get this value here, and then I divide that out. If you look at this data sheet here, you'll notice that it told us the short circuit ratio of 0.480. I haven't used short circuit ratio all that much. It doesn't seem to be, I don't know, super duper useful to it. I've seen it. It's always specified. I wonder if it's even specified in here. Anybody see it when we scroll through? Let's see. See. Lightning impulse. We have kind of interesting here. This tells you a three-phase short circuit. And it tells you, I guess, maybe what the force would be under on the stator bar conditions. So under a three-phase short circuit, it tells you how much force is applied in inch pounds on the stator bars. Current density, take a look at the current density. This is amps per square inch, so you can get a sense of that. Line losses. But I don't see a short circuit ratio calculated here. Yeah, those are the actual short circuit currents under, like, if you actually put a short circuit on the terminal, that what you would get is the value. Okay. So again, I don't know how useful that parameter is, but we just explained it in case you need to see it. Okay, go ahead.
Can you go back? What does the bottom one say for the IF?
IF at voltage rated. That's the field current to get rated voltage on the open circuit characteristic.
Because it says IF voltage rated up top, right? So
Where?
yeah. Oh, IS rated, ISC rated. What it says?
This is the short, this is the current, the rated current on the short circuit characteristic. This is the voltage, the rated voltage on the open circuit characteristic. So in the case of the generator, you guys doing the homework, this would be 13.8 kV. And this would be 12,844. The field current has to be whatever it is. And maybe, let's see if that information is available here. Those are short circuit currents. Core losses. So I can see rated field current at rated voltage and a certain power factor. That's not what I'm looking for. Yeah, it doesn't have that data in here. So you don't actually can't even calculate short circuit ratio on this. I mean, it has it for rated field current at rated voltage, but that doesn't tell me necessarily if that's on open circuit characteristics or not. So I don't know. It does say, let's see, rated field current at certain power factors. Yeah, it just doesn't tell us enough information to be able to make that determination. So we couldn't calculate it based on this Northfield one there. Okay, so let's do our example here. We've got a fairly small generator, at least compared to 1500 MVA. I have a 0.2 MVA, 480 volt, 60 hertz, 4-pole machine. It's Y connected. It was run at 5 currents and 5 amps of field current. And we got an open circuit characteristic. Well, not even a characteristic, just an open circuit test. We got 540 volts at rated field current. And at 5 amps of field current under short circuit conditions, we got 300 amps. Then we did the DC test and we applied 10 volts and we measured about 25 amps across those. So the very first thing we need to do, item number 1, calculate the speed of rotation. The only thing I need for that is it's 60 hertz and it's 4-pole machine. So what is the actual speed of rotation? You don't even have to do any calculations. It's a 4-pole machine, which means it has 2 pole pairs. 3,600 divided by 2 is 1,800. So this is an 1,800 nominal RPM machine. This is what it's designed to rotate at. Now we have to do the equivalent circuit parameters, and we can do them here, but let's show us the work that we've done here. So here's our electrical frequency, how we did the calculation there. We're going to go ahead and do our open circuit test. We've got 540. So this is a Y-connected machine, like that. I'm measuring 540 volts under the open circuit conditions. If I want to measure if I want to get the impedance across an individual phase, then I have to take the 540 and divide it by the square root of 3, right? To get the individual phase voltage. So when I do that, I get at open circuit conditions at 5 amps of field current, I get about 312 volts. So the open circuit characteristic at IF equal 5 amps is 312 volts. Okay. The next thing I need to do is I've got to go ahead and calculate or obtain what the short circuit value is. Well, the short circuit, it just tells me directly I short circuit at IF equals 5 amps is equal to 300 amps. So the magnitude of Z at IF equals 5 is 312 divided by 300, which in the calculation is 1.04 ohms. Okay. So I have 1.04 ohms. Now I've got to tease out the value of RA, and I can get that from the DC test. So here's my DC test, Y connected. I've got 10 volts DC, and my current is 25. This is RA, and this is RA. So 10 over 25 is equal to 2 RA. So RA is equal to 10 over 2 times 25, which is equal to 0.2. To calculate X sub S, I plug that into here, and I end up with 1.02. So to do an exact calculation, I get 1.02. To do an approximate calculation, I could just say that these two are the same. Now, there's one other thing that's a little subtle in here that I mentioned that might not be obvious to see. Why did I call that saturated? Any idea why I called it saturated? Well, the nominal voltage of the machine is here, right? The actual test value I did is way up over here because it's nominally rated for 480, but we got 540 volts. That's well above the nominal rating of the machine. And since all our machines are designed to operate at least somewhat partially saturated, we know to get to 540 volts, we're pretty well saturated to be able to do the calculations. So I sneakily said it was X or ZS saturated, not unsaturated. To do unsaturated, you might have to know that this voltage here, if that was like 300 volts, okay, that's most likely going to be unsaturated because it's way down at this point, right? It's well below what the nominal voltage of the machine is going to be. So we're feeling pretty comfortable that we can get that value. Okay, questions on that? So now let's take that machine and let's put it through its paces. And let's calculate what the voltage regulation is going to be of this machine under a couple of different conditions. So we have a load current of 100 amps at 0.8 leading, lagging, and unity. And then we're going to calculate all these different powers. And then we're going to see what happens if our voltage regulation is there. So let's go ahead and go over to whiteboard and draw our circuit. Oops, come on, wake up. Can you not wake up? Okay, so here is my voltage source. I'm just going to go ahead and ignore, right, our value. And then I'm going to tuck a load on it. And the load is either going to be 100 amps at 0.858 power factor lagging, leading, or unity. Okay. So the first one I'm going to do is 100 at 0.8 PF lag. Okay. This voltage here, because this is nominally rated for 480 over the square root of 3, I'm going to put my terminal voltage to be 480 at a square root of 3, right? Divided by the square root of 3 at an angle of 0. That's the value that I need to do. Because I'm trying to calculate what that current is, and I need a voltage to be able to calculate the current, so I can calculate what EA actually is going to be. So 100 at a 0.8 power factor is 100, that's I, 100 at an angle of inverse cosine, oops, of 0.8. Notice I have the negative up front here too. Why? Because it's a lagging power factor. So to calculate EA is going to be equal to 480 divided by the square root of 3 at an angle of 0 plus J 1.04 times 100 inverse cosine of 0.8. Let's put that, I'll just do it in MATLAB. If I can find MATLAB. Whoops, that was not MATLAB. Oh, the hand shook me to no man's land again. So sorry for the technical issues. I think that's the first time it's ever done it twice in a class. What's that?
Have you put in a ticket for media services?
That means you, right?
No.
Here, do you need a piece of paper that says, you know, you can do that? Yeah, that was the second time. Anybody wants to come up and see, I'm not doing this to be goofy. It just is acting really weird. All right, so my excess is going to be equal to J times 1.04. My VT is always going to be equal to 480 divided by the square root of 3. That's at an angle of 0, so that's might as well just say 277, whatever. And now I've got to go ahead and solve for the current. So I'm going to call it I lagging is equal to 100. And this is how you have to enter it in MATLAB, right? This is times EXP, because we have to use Euler's identity. Negative J, because it's a negative theta, times the inverse cosine of 0.8, I believe. Right? That was our first one. Let me check. 0.8 lagging. And so my EA, oops, not EAA, is going to be equal to VT plus XS times I lag. Not looking really good, right? Because when we do voltages, we like to see them in magnitude and angle. So I'm going to display my EA. And that's going to be equal to the absolute value of EA and the angle of EA times 180 over pi. So I get 349 at an angle of 13.76. So my percent voltage regulation calculation What is the value again? V no load minus V full load all over V full load times 100%. That's another way to say EA minus VT over VT times 100. So in the case of a lagging power factor, what I'm going to end up having is VR lag is going to be equal to my EA, which I want as my absolute value, right, EA. I can't do the whole part because I'm just looking at magnitudes, minus my VT, divide that by VT, and then I multiply by 100. So this has a pretty big voltage drop, right? It's 26% change in voltage if the load goes away. How about looking at what's called leading power factor? The only thing that needs to change is this, right? So I'm going to call this I lead. And now this becomes a positive number, right? All the calculations are going to be the same. So let's display EA. Oh, I got to calculate it first, sorry. Now I'm going to display it. And look at the voltage. It went all the way from 349 down to 230. It is less than the terminal voltage. And that's because reactive power flows from a higher magnitude to a lower magnitude. In the first case, in a lagging power factor, reactive power was going from the generator out to the load. In a leading power factor, the reactive power is flowing from the load into the generator. And the way that you can verify that is the voltage. It went down to 230. Now, if I'm going to go ahead and do my calculation for voltage regulation, now I'm going to get a negative. The voltage is going to drop by 17%. And then the last case is unity. I'll just do this unity. And all I need to do here is get rid of this, right? Because 100 at an angle of 0, just 100. So I'll do my calculation again. EA is here times unity. I'm going to display that. And the voltage now has gone up to 296. Why is that? Well, it had to go up because remember, this here is absorbing or eating some of the reactive power, using some of the reactive power that's being supplied by the generator. So under unity power conditions, this right here is absorbing Q. It's taking reactive power in and it needs it to support the terminal voltage. But if I look at my voltage regulation, unity here. Oop. Oh, come on. Please, Louise, I gotta find the right one. Let's do unity. Now the voltage only would float up by 6.8%. Okay, so a slight change in the voltage, but a lot more manageable. So if I go back to my problem description, I've got all three cases. How do I calculate the real and reactive power in there? That one's pretty easy, right? It's always going to be square root of 3 times VI conjugate, because this is the line quantity and this is the line quantity. So S lag is going to be square root of 3 times 480, which is at an angle of 0, times I, which is 100, at an angle of negative cosine inverse 0.8. Have to take the conjugate of that. Leading, this is exactly the same. But this becomes a positive 0.8 conjugate. And S unity, really easy. There's no angle, right? With the current, it's at unity power factor, so there's no conjugate to take. So you can take those three, and then you can calculate the P and the Q for each one. Does anybody want to see me calculate those out, or do you want to do those on your own? It's up to you. Sure. So I'll go back to MATLAB. So S lagging is going to be equal to square root of 3 times 480 times 100. Actually, I got to take the conjugate of 100 times e to the negative j inverse cosine of 0.8, right? Do I have too many? Not enough. Square root of 3. Yeah, I need one more. So P lagging is 66,051. Q lagging is positive, right? So when I do my power triangle, it goes, the power triangle should be for this one, should go look like this. The power triangle for this one should look something like this. And the power triangle for this one is just a straight line, right? So we see that we get a positive 49 kvar. We'll do it for lagging, or for leading, sorry. And the only difference is this becomes a positive J, not a negative. So same number, but now our Q goes down. And that makes sense, right? Because the power factor, which is the ratio of P over S, is always 0.8. So there's no change. And then we'll do unity. And then all I need to do here is take this out and then just make it 100, because the conjugate of 100 at an angle of 0 is 100. So that's 83 kW with 0 kW. All right. So those are the real and reactive powers for the load. Notice that's not asking the question, what does the total machine deliver? Because the machine itself internally needs some reactive power, but normally we don't worry about that. The machine is responsible for doing what it needs to do. We're just focused on, what the load is. And that's why when we talk about, if you look at these data sheets, remember how it said it was operating up to a 0.9 lagging power factor? Where was the value for 0.9? Oh, maybe it was on this one. Let me check. Yeah, you see it says 0.9. That means that that machine can deliver rated power, whatever the rated power is 150 MVA, up to a 0.9 power factor, either leading or lagging. Anything beyond that, it might not be able to meet. So if you wanted to run it at a 0.85, leading or lagging, not going to work, or it's not guaranteed to work. And so that's why our friends in the utilities say, hey, if your power factor at your site is really bad, you're going to pay more money, because we have to do a lot on our system to make that work. Most generators are designed to operate at 0.9 leading or lagging. Some of the cheaper ones are designed to go to 0.95, but it just depends on the utility. Some utilities will say, that's fine, but you can only sell power to us at a 0.9 lagging power factor, which means if you've got a 10 megawatt capable generator at 0.95, you have to back up the amount of real power that you can sell to the utility until you get your power factor to be 0.9. Con Ed used to be really bad about it. Con Ed used to have a requirement of 0.85. Con Ed is the utility for New York City. So they were really, really tough about it, because it was 0.85 lagging or leading, and most generators weren't made for that. So a lot of people had to do a lot of work to do that.
I thought everything in New York was managed for the New York Power Authority.
NYPA? New York Power Authority, I think, manages like the high voltage transmission.
Oh, they don't care.
Well, Con Ed has some, medium voltage stuff, 138 kV, that type of stuff. But most of the high power stuff in New York is done by NYPA, which is like, it's the same, kind of the same thing for Maine. There's a company called MEPCO, which is like the Maine electricity power company. And they're kind of responsible for sort of helping to manage the grid, because when you leave Orrington, and I don't know how far out, that is owned by Versant or managed by Versant, but at some point it becomes CMP. So MEPCO kind of helps coordinate everybody. In New York, it's much harder because in Maine, what do you have? You have Versant and you have Avangrid or CMP. And they take care of pretty much all the high voltage stuff. But once you get down to the distribution levels, those can be all the different utilities. That's why you can have an Eastern Maine electric co-op, or you can have a Holton Light and Power, or Kennebunk Light and Power. You can have smaller munis that help take care of Madison Gas and Electric. For those of you who are familiar, a little bit closer here, they have their own power supply. But the grid, it becomes so complicated. And in New York, you have Niagara Mohawk, you have Public Service Electric and Gas Long Island, which used to be called LIPA. You have Con Ed, you have National Grid, and I think there's one other one. So you got all these different companies, and they're all trying to make sure that the power delivered in New York is reliable and as cost effective as possible. And because they're all interfacing with each other, NYPA sort of manages like the high voltage transmission. So I think they manage all the 345 kV. So that's my limited, I know a little bit about it because I've worked on some New York stuff in the past, but I think that that's typically what they have.
Connecticut is still on grid, but it's UI.
Yeah. Yeah, so Avangrid, so CMP was its own entity, and then it just got bought out by a bigger conglomerate. And so they decided to keep the names as the individual companies they bought out. So Avangrid bought CMP and they bought UI. I think they also bought, what's the company? National, they didn't buy National Grid. There's a company in New York that they purchased some of the utility stuff. And so it's basically just like, it's a conglomerate. What's that? No, absolutely not. They don't have a monopoly because in Maine you have Versant, which is its own company. In New York, I mean, in New Hampshire, you have PSNH, Public Service New Hampshire. I think that's the only one there, but that's actually Eversource. Eversource is mostly in Connecticut.
Yeah.
And some in Massachusetts, because Western WMECO, which is Western Mass Electric Company, I think that's an Eversource entity. And then you have in Rhode Island, I think that might be UI. I'm not sure it's in Rhode Island. It's pretty small. But yeah, they have 3 or 4 bigger players. But utilities themselves are monopolies. Like if you're from Connecticut and you might be in UI territory, all those customers are managed by UI. And so since it's an obvious monopoly, that's why you have public utilities commissions that says, you got to follow our rules or else you get put out of business. So they are a monopoly, like not the parent company, but the individual utility, but all that stuff is regulated. Yes. Yep. They have to follow the rules. Like they can't, at least in Maine, you can't just change the rate without getting approval by the PUC. So you have to document it, prove why you need to go up. And then if they approve it, then you can increase your rate base. If not, you're out of luck.
Where does that PS code nomenclature come from?
The what?
The PS code.
MEPCO?
PS code?
PSCO? Oh, that's Public Service New Hampshire, PSNH.
Right, oh, sorry, I'm thinking of, I'm getting home, sorry. In Colorado, they have PS code, the Public Service Colorado, that's in by itself. Where is the PS?
Just what are they actually doing? They're serving the public, right? Because PSE&G, that's Public Service Electric and Gas, that's headquartered in New Jersey. And then there's let's see, it's PG&E, Pacific Gas and Electric. Some of them are public service ones, but a lot of them are the actual names of the company, like PG&E, Public Pacific Gas and Electric. That's where you get a little more of the individual names. So it's just, how they wanted to start off. These companies are almost 100 years old. So when you say public service, that sounds like you're doing really good things for the world. So why not call me public service? But that, you don't see that name very much. If you went to PSNH and say, what does PSNH stand for? It stands for PSNH. What do you mean? What does it stand for? But it's Public Service New Hampshire, which is actually owned by Eversource. And Eversource is not even Eversource. You know what the real name of Eversource is? Northeast Utilities is what it used to be called before it became Eversource. So it was rebranding. That's all it is. And then Boston now, which I think is under Eversource territory, used to have Boston Edison. It's an old city, so they had an Edison affiliate, and they were Boston Edison back in the day. So you can still find prints that say Boston Edison. You look around enough. And then is the load current. So this is just a question. If the load current is decreased from 100 amps to 50 amps, will voltage regulation improve or get worse? It would improve a lot, right? Because you have less voltage drop. The voltage, whoops, here, that drop is going to be reduced. So if you compare it from 100 amps to 50 amps, even if the power factor is the same, you're going to get less voltage drop. So one of the things that you can do, if you are dissatisfied with a voltage regulation of 26%, where was our 26% for, oh, sorry, 16%, right? If it's 16.9%, if you're dissatisfied with it, just go ahead and say, all right, well, we can't run 100 amps of load. So we need to run it at 50 amps of load. And that is one of the things that sometimes power systems are limited by, which are not necessarily the technical things, which I'm going to burn the conductor up. It could be like, I'm worried about too much of a voltage drop. If the system goes down, then that voltage flows on the system so high, and then I can cause fires in people's homes. So they can limit it. So a lot of the system is actually, the grid is limited not by the power ratings of the equipment, but by more, more administrative things, if you will. All right. Let's see. I think that's it for the slides. Questions? I think that finishes chapter 4. So you have a couple homeworks. One, hopefully a pretty easy one, right? If you look at the curve, you might find some clues and some hints of how to do it. Then the other homework. Go from there. Question for me? Going once, twice. All right, well, guess we're sold. So that's all I had, everybody. Have a great day. And if I don't see you, have a great weekend. Talk to you all on Monday. Take care, everyone.